Imagine having the absolute superpower to predict the future. Well, at least the future of how things move. Whether it's a sports car launching off a starting line or an object plummeting from a terrifying height. Today, we're diving into this explainer to uncover Sir Isaac Newton's absolute cheat codes to reality, the equations of motion. So here's our roadmap for this explainer. 1. The blueprint of motion. 2. Meet the SUVAT variables. 3. Deriving the equations. 4. Special cases in motion. 5. Real-world physics. And 6. Visualizing the big picture. Let's get right into it.
Part 1. The blueprint of motion, the foundation of classical mechanics. Moving to Section 2. Meet the SUVAT variables, the cast of characters. Now, you really can't use these cheat codes if you don't know the buttons to press, right? Formulated by Sir Isaac Newton, these equations govern exactly how objects behave when their acceleration remains steady and constant. We often call them the SUVAT equations, named directly after the 5 key symbols you've got to know. S stands for displacement, measured in meters. U is our initial velocity, and V is our final velocity, both measured in meters per second. A represents acceleration in meters per second squared, and finally T is time, in seconds. Master these 5 variables, and you've literally got the keys to the physical world.
All right, Section 3. Deriving the 3 equations. No magic, just logic.
Here's the very first equation we're tackling. V equals U plus AT. It beautifully connects your final velocity to your starting speed, your acceleration, and the time that's passed. But, where exactly does this formula even come from?
Well, I'm going to show you that it's just a logical rearrangement of stuff you already know. Step 1. Take Newton's basic definition of acceleration, that it's the change in velocity over time. Literally, A equals V minus U all divided by T. Step 2. Just multiply both sides by T. And step 3. Rearrange those terms to isolate your final velocity. Boom! You get V equals U plus AT. Seriously, no magic, just pure logic.
Moving right along, we hit equation 2. S equals UT plus 1/2 AT squared. This one relates displacement to initial velocity, acceleration, and time. It's basically your ultimate go-to tool when you absolutely need to calculate exactly how far an object travels while it's in the middle of speeding up or slowing down. Let's see how this builds so beautifully on that first equation, transforming average velocity into a powerful distance formula. Step 1 tells us displacement is simply average velocity multiplied by time. Simple enough, right? For step 2, because our acceleration is uniform, that average velocity is just U plus V divided by 2. Now, for the magic in step 3, you just substitute equation 1 right into that V spot. After a tiny bit of algebraic cleanup, you land precisely at S equals UT plus half AT squared. And that brilliantly leads us to our third equation. V squared equals U squared plus 2AS. This relates velocity, displacement, and acceleration. But look closely. Do you notice what's completely missing here? Time. Equation 3 is your absolute secret weapon when you know the distance an object traveled, but you have no earthly idea how much time has passed. To get here, we confidently combine our average velocity method with equation 1, completely eliminating time from the picture. We start with that average velocity formula for displacement. Then, we take equation 1, rearrange it to solve for t, and plug that right in. We won't get bogged down in the heavy algebraic weeds here, but by using a classic identity to cross-multiply and rearrange, we are left with v squared equals u squared plus 2as. So the big takeaway here is this master toolkit. Notice how every single equation purposely ignores one specific variable. Equation 1 ignores displacement. Equation 2 ignores final velocity. Equation 3 entirely ignores time. All you have to do is identify the one variable you're missing in your real-world problem, and this toolkit tells you exactly which equation to grab. Section 4, Special Cases in Motion, Changing the Starting Conditions. Now let's explore how wonderfully simple this math gets when our real-world conditions shift. Notice this striking difference here. Whether you are absolutely mashing the gas pedal from a standstill or you're slamming the brakes to a dead halt, the math effortlessly adapts as variables drop to 0. If an object starts from rest, that initial velocity u is 0, instantly shrinking equation 1 down to just v equals at. On the flip side, if an object stops entirely, final velocity v becomes 0, completely changing the algebraic layout. It just simplifies everything. And honestly, this is one of my favorite applications. If you drop an object in a vacuum, it enters free fall.
Gravity takes over as a constant acceleration of 9.8 meters per second squared, instantly streamlining all our formulas. Because your initial velocity is 0 and your acceleration is just gravity, equation 1 cleanly becomes v equals gt. The math seamlessly molds itself to perfectly describe the literal pull of the Earth. So, having conquered the theory, you're probably asking yourself right now, how do these formulas actually help us decode the physical world around us? I mean, it's great to have equations on a whiteboard, but what can we practically do with them? Well, let's find out in Section 5, Real-World Physics in Action, Putting the Math to the Test. It is time for the dramatic payoff where we actually use these equations as cheat codes for some thrilling real-world scenarios. Imagine a car rapidly accelerating off the starting line. We plug in our 0 initial velocity, an acceleration of 3 meters per second squared, and a time of 10 seconds right into equation 1. We're hunting for the final velocity, and we have the time, which makes equation 1 the absolute perfect tool for the job. And boom, the math reveals a blistering final velocity of 30 meters per second. Just 0 plus 3 times 10. It's incredibly straightforward, but this is the exact logic automotive engineers rely on when they're designing launch control systems in high-end sports cars. Let's look at an even more extreme example. Say we drop an object from a terrifying 80-meter cliff. We can use equation 3 for this, simply because we don't know the exact time of the fall. What we do know is that initial velocity is 0, our displacement is 80 meters, and acceleration is gravity, so 9.8. By relying on gravity as our acceleration and plugging those exact values into v squared equals u squared plus 2as, we discover a massive impact speed of 39.6 meters per second, all calculated instantly, entirely from safety, without ever having to risk dangling over that cliff with a stopwatch. Finally, Section 6, Visualizing the Big Picture, Graphs and Rules of the Universe. Let's pull back from the raw numbers for just a second and look at the big picture of what all this uniform motion actually looks like, visually. Always remember that uniform acceleration creates a beautifully predictable straight line on a velocity-time graph. And even better, the physical area underneath that straight line gives you your exact displacement, which is exactly what equation 2 calculates. Meanwhile, on a displacement-time graph, that exact same motion forms a beautiful, sweeping parabola. The raw math and the visual geometry are just perfectly linked. Isn't it completely fascinating that all uniform motion in our vast universe, whether it is an apple falling from a branch or a rocket boosting up through the atmosphere, is tightly bound by these few, elegant, unchangeable rules? Newton's equations aren't just dry textbook formulas. They are the invisible geometry of our reality. So, now that you possess the ultimate cheat codes, how will you see the moving world differently today?